Memory map specifiers is a term that I coined to explain the concept better. That is, the linker takes in information from some file which lets it know about the memory map of the target board and where to place which section of the output. Commonly, it is called as a linker script. So, henceforth, we will call it a linker script, and the linker script has an extension of .ld, which is a convention. Here are some points that I've made about linkers, something that we have already discussed. That is, memory layout of ARM Cortex-M based controllers vary between different vendors, and the linking process has to account for the same. So ARM Cortex-M microcontrollers the have various memory layouts depending on the vendor and the application. It can have different RAM sizes. It can have different flash sizes. The flash may start from different memory addresses. So the linker needs to be told about the whole thing before you can run the linker, so that the output binary is properly generated from the object files. Like though the general layout is the same, but the vendors can move around the addresses within the designated areas as well. Okay, the flash memory RAM starting address size differs from different chip vendors. For example, Texas Instruments and ST varies in their memory layouts. The linker script contains instructions which combines multiple object files into one. We spoke about that previously. And the major tasks of a linker are, so these are the major tasks of a linker, and which we'll see individually, are storage allocation, symbol management, library management, symbol and segment relocation. So when you have a source file with some symbols being, the address is not resolved, or for the entire segment or entire section of that particular code may not have the right, say executable code may not have the right memory location assigned to it, because all memory locations, every individual file we have starting memory locations to be 0 and so on. And the linker resolves all that through storage allocation, symbol management, library management, symbol and segment relocation. The linker combines multiple object files into one, and the linking process is a two-stage process. So it's a two-pass process. Now coming to ELF object files. Now this is the file format that the compilers create in their .o files or the output files. So the object file mainly contains 5 kinds of information. It has a header information, which is overall information about the file, such as the size of the code, name of the source file, it was translated from, the creation date, so on and so forth. So this is the header information. Then you have the actual code in that object file. For example, the binary instructions and data generated by a compiler or assembler. So whatever we are seeing here, the object file has not yet gone into the linker. That is the individual object files that are generated by the compiler. Okay, so the linker will be taking in multiple object files, and it is going to be combining them into one, as we read. Relocation, so it's a list of places in the object code that have to be fixed up when the linker changes the addresses of the object code. So you have the object code, the binary instructions, and then you have a relocation section which gives the linker information about the symbols and that have no addresses assigned to them. So those addresses will be needing fix up. So that is the relocation section. Then you have symbols. So symbol section will have global symbols defined in this module. Symbols to be imported from other modules or defined by the link. So symbols will be your global variables and function names. Okay, not local variables. Global variables is considered as a symbol. Function names are considered as symbols. We'll see that shortly. Then comes debugging information. So debugging, we discuss this. Debugging information is other information about object code not needed for linking, but for use of a debugger. So this debugging information is retained by the linker if we need to debug the code. That is, if we compile the code with a -G option, the debugger information is included. So this includes the source file and the line number information, local symbols, descriptions of data structures used by the object code, such as C structure definitions, and so on. So this is optional. You may or may not have the debugging information. And then you have, and there are multiple ways of taking the object file dump. We will use objdump and readelf both. Now this is the ELF structure, ELF file structure. So we saw the different parts in the previous slide. So by Wikipedia, the definition is ELF is executable and linkable format, formerly named as extensible linking format, is a common standard file format for executable files, object code, shared libraries, and core dumps accepted among different vendors of Unix systems. Okay, so that's a definition from Wikipedia. So like we saw, it has a header information, then it has a section header information, which again links to the object code, the relocation information, symbol table, and debug information. So this is how it is. The section head, there's a header, there's a section header. Section header has links to all of these sections. So this is a ELF structure for the object files. So the object files are organized in this way when you run a compile using ARM GCC. Now this is how the ELF header looks like, but we will stop here, and we are going to run the compiler. We are going to get an object file first, and as we said, we'll do it manually. We will write the GCC command to actually generate the object file for all the files that we discussed about, the 3 files that we are going to work on, and we will inspect the ELF header there as well. So let us go to the command prompt and put in the command for running the GCC for this particular architecture, that is ARM Cortex-M. Let's do that. So we have the command here, and the command is ARM none AVI GCC. That is the GCC for ARM, and these are some options. The options are -C is only to compile and not to link. So it will just create the object code, but it will stop at that stage. It will not link. And then -G is to include debug information. -I is just informing the compiler of where to search for the includes. That is the header files. So we add include paths like this, and in the examples in the slides, you will see that I have not added this include path, because I had kept all the header files in the same location. So we'll go by that, but let us have this includes in the commands. It doesn't make any difference for the purpose of what we are seeing it now. The optimization level we have kept as 0, but you can have different optimization levels up to 3, and then OS for code size. We'll keep the optimization level 0 because the assembly that comes out of it is easy to understand, and since we are learning about this, I don't want to complicate things. So let us keep the optimization level at 0. Now CPU is what CPU you are compiling it for, because ARM GCC can compile for multiple different kinds of ARM CPUs. So CPU is Cortex-M4, and we are compiling for Thumb because ARM Cortex-M4 is Thumb 2 architecture. So that is why we have this word here, we have this keyword here, and then it is not using any start files, and this means that it's using the hardware floating point. So mhard float is using the hardware floating point for the compilation. So what this does is, when you say ARM Cortex-M4 has a single precision floating point unit, okay, so a single precision float, if you give mhard float and you declare float something, say you do float float, say x equal to 2.35, and then you do float y equal to 5.66, and then you do float z equal to y star x. Basically what happens here is that this instruction, not the previous two, but this instruction will issue any such instructions which have float will issue create assembly instructions. The compiler will be creating assembly instructions which will be specific to the floating point unit of the controller. If you are declaring float but you have not used mhard float, still the compiler works, but the instructions it is going to generate will be without using the floating point. So it's going to generate software floating point instructions, and the disadvantage in that case is it is going to take longer time to complete the calculation, because the entire calculation is going to happen in software. So that's one thing that you need to know. Now, so after float we have MPFU, that is what is a floating point unit version. So we can put in different versions for floating point unit. The one I have here, it could as well be different, but right now I have just kept it as VFP v4, which works fine. And then we have the file that we are compiling. So build example main.c is one file that we saw. We give -o, that is we want to create the object file, and this is what the object file name we want it to have. So when we compile it, we get some warnings, because this demo relocatable function has not been declared. But nevertheless, let us not worry about that, because this does not hurt the this will not hurt the linking process. Let us not bother about this right now. So as of now, we have generated one object file. So if you want to view the object file, it is here. So if you go to the, so it is this object file that has been created, build example main.o. Okay. So now we have just got the object file now, but if we have to check what are the contents of this object file, then we'll have to run those two utilities that we saw, that is objdump and read elf. So first let's try to check out the elf header for the object file that has been created. Okay, so let's do read elf, and -h option is for the header files that has extract the header file information, and then we will have to give the output file in, that is build example main.o. So we do the example underscore .o. So what we are going to, I'm not dumping it into a file. I'll just show it here only. So this is the header information for that particular, for this particular build example main.o. Okay, this is not the header file of the final output. Okay, so the ELF header that we spoke about, it has a magic number to begin with. Okay, and then after the magic number, you have the class which says it's the ELF 32-bit, what kind of data it is having. So it has a 2's complement little endian, version is 1, OS application binary interface is Unix, system 5, ABI version is 0, type is relocatable. So relocatable is an important part. Relocatable means whatever address locations this file has been compiled with, which it can be moved. So if say the addressing starts from 0 here for this particular file, you can file can be moved around, and the address locations can be changed for fixing the function calls and fixing the global variables. So that is something that is possible here. So this file is a relocatable file. The addresses are not absolute in this. We'll see that. Version, entry point address, start of program headers, start of section headers, how many bytes into the file, okay, flags, size of the header, size of program headers, and so on, number of section headers. So 21 section header, string table index is 20. So this is just to show you that there is a header information, and it gives you different kinds of information for your consumption. When the source code is compiled, the compiler creates the ELF file which contains the compiled code along with various other information and that is something that we have discussed about previously. Now, once the code is compiled, the output file or the .o file, object file, is going to be neatly split up into multiple sections. Now, like .text, .rel.text, data, VSS, RO data, debug info, and so on. So this is done by the compiler. So this split is done by the compiler, and the section, we are just looking at the section headers part of the ELF file. So the section headers table is actually giving an information of all the sections that it precedes. So there are many sections coming after it. For example, the .text section, the .rel.text section, data section, VSS section, RO section, and so on and so forth. So this gives a memory map of that section, of those sections, and talks about and provides some more information about them. Now, this information can be extracted by readelf utility, and of course by objdump as well. Now, we have used the readelf utility to extract this information. This could also be extracted using objdump. So you are free to use any utility. Now, as we can see, there are multiple sections here. So the compiler knows, when it sees the code and it compiles the code, it knows what to place where. For example, it can recognize code and place it into a section called .text. Now, these are some conventions that the compiler follows. It is these conventions are not given by you. These are some standard conventions that the compiler follows. So code is in .text, and then data, say static or constant data, that or if you have declared some data as static or constant data, initialized data actually rather. So rather, initialized data, whatever you have, will go into the data section. Okay. So here you will have initialized data. That is already when we start running the program, some initialized data values go into this particular section. For example, if you do int a equal to 10, okay. So when the program starts, this value eventually has to go onto the RAM, but so we'll see that the data, though this has to go onto the RAM eventually, this has to be first saved into the flash and so on and so forth. That's a different topic of discussion, but this is where you have initialized. This section has the initialized data. Then you have the .bss section. Now, .bss section is again a section that is created by the compiler, and .bss section has uninitialized data. Okay. So something like you declare int a or int a equal to 0, that is going to go into the .bss section. That is the uninitialized and zeroed out data are all going to go into the BSS section. Now, RO data is data that is constant. So there is some data that you declare as constant. That is, for example, constant int a, for example. Okay. So when you have a constant keyword, in front, those such data is going to go and sit into the RO data section. For example, if you see here, this data goes and sits into the RO data section. For example, you have the constant mentioned here. Okay. Now there will be other initialized data also, which will again go and sit into the data section. So we'll see all that. Okay. We'll see all that. We will change this particular code, and we'll see how the data moves around and so on and so forth. So coming back to the slide. So this is the layout of the sections that come after it. Okay. So you have address. So for example, say for the text section, type, it says proc bits. Proc bits means it has got to do with program. Okay. Address is 0. Offset, it starts from this offset, that is 34 hex, and then the size of it is 5C. And then we'll look at the flag attributes. So attribute means A means it is allocatable, and X means it is executable. I means it is only for information. For example, relocatable section has I would mean that it is just for information. WA means it is, you can allocate, and this section is writable. .bss is also writable. So these writable sections go into the RAM. Now this section is only A. Okay. So so this is only allocatable, but this section is not writable. Okay. So this way we have attributes for all the sections. So this is an output from the compiler, which the linker reads, and it gets the memory layout first. So for each file, so for example, we have three C files that we are working on. That is the main and the core initialization and the startup GCC file. So all those three files, each of these files will have an ELF file generated, .elf.o file generated. Each of these files will have separate section header. So now these section headers of course will look different, because these will be the same, but the offset and the size will be different. The addresses will all be zeros for now. Okay, because the offset takes care of this. So addresses will be zeros, and you'll have the offset which talks about where all the data is going to go into. That is offset from address 0. Okay, but we know that we'll have to flash it in a different address location. So this is what the linker gets, but it'll do some activity on this, and when we look at the final section header, it'll look very different from this. The address will change, the offsets will change, the size will change, because that time it is going to merge all the three object files from the three C files, and then it's going to create a different it's going to create a section header which is a summation with, of course, alignment correction and so on, and the section header is going to look different. So say this is section header for one file, then we can see a different section header for a different file. So we can actually have a look at the section header if and you can try this out for your exercise. So let's rub this out and let's have a look at the section header, how we can see the section header. Okay, so we'll start from here. We'll just compile the build example main file once again, and we'll start from there. So this is the command for compiling the build example main file. And just as a side note, I have created a command file for this particular segment where all the commands are given. That is, all the commands that I'm going to use here for compiling my code and checking the ELF file. So I will be uploading this along with the material. So when you try out this exercise, you will also have a reference to work on. So now, so when we compile it, we get the object file. Okay, that is the build example main.o. Now what we'll do is we'll just run a readelf for now, and we'll just see the same information whatever we saw in the slide. So we do readelf -s for section headers, and then do a build example main.o. Okay, so this is wrong. Build ld and then example underscore main.o. Okay, so this is going to give us the section header whatever we saw in the slide. So check this out. So this is the same section header that you saw in the presentation. Same thing. So this is how you get it. So now if you want to see the same section header but you want to see it in a different way, that is you want to see it using objdump now, suppose. Okay, so if you have to see it through objdump, then you'll have to issue a different command. So the command goes like this: arm none eabi objdump -x. So let's do away with the -x command right now. Just let's look at only the section headers like the readelf and see what we get. This is showing the same information as what we saw previously. The section headers convey the same information as readelf, but then the layout is slightly different. For example, the attributes that we saw in the case of readelf was through flags, and they were placed in different columns here. In the case of objdump, we get the same information, but it is in a different format. And there is one information that is not visible in the readelf, and that is the VMA and the LMA values. That's an interesting concept actually, and that is heavily used when writing our linker script file. So this is how you can look at the section headers in multiple ways, that is using readelf and also using objdump. Now if you want to see similarly if you want to see the section headers for the other two files, what you need to do is you need to compile those files first. So say we compile the second file, that is the core initialization file. So if we just compile that, and it's the same process again, that is we do a compile, and once we do a compile, we'll have to run either readelf or objdump. So if we do readelf, say we want to see section header, and then we do .o. So let's okay, so this is a section header that we'll again see. Now as you can see, this is a different section header. It is not the same as what we saw for the main, because as you can see, the offset is different, the size is different here. Okay, so this is a different section header. So when the linker is fed with this particular object file, it will again gather information from here, and the meaning of these flags are pretty much the same. The compiler has again split up the file into or it split up the source file into multiple sections again, text, relocatable text, so on and so forth. So that's pretty much the same. The flow is pretty much the same, but the information is different. The data here is different. Again, you can have a look at this file in the different format, that is you can use objdump also. Now let's look at the third file, that is startup GCC. So we can also look at the headers for that particular file. So we can do readelf again, and let's do a -s, and then we just do startup instead of gcc.o. Okay, and then let's check out the file that the output that is generated. So what we see here is, again, we see this same kind of section header, but again it's a different offset starts from 34 anyway, but then the size is different. So the size here, the size is higher, here the size is lower. So since the size is higher or lower, then the offset will vary. A5A, it is 1B04, and here you have a different offset, because depending on the size, the offset will also move along to create the space, and so on. So these are the three section headers that we have observed. Now, when we feed these three section headers, the linker makes a note, and it stores this section headers into some data structure within the linker for actual linking of the code into an output object file. Okay, so this is how it is done. So if you want to investigate, these are the commands that you can issue to view the section headers. So this is only the section headers. After that, we will touch upon the different sections. We will look at how the text section or the relocatable section, how they are organized and what to expect from them.